So I welcome you boys and girls, ladies and gentlemen, to the discussion on true solids. True solids have a definite melting point, and of course their particles are closely packed as if one is touching the other, and in the arrangement is such that they have short range as well as long range order in the arrangement of particles, and they are said to be anisotropic. Anisotropic means they have different properties in different planes, and they have a definite cleavage pattern. They will cut in certain patterns. Whereas the pseudo solids are the other variety about which we don't talk, like talcum powder, clay, and some gels, and they don't have any definite melting point. Even glass is not a true solid. Even glass is not having any sharp melting point. In glass also there is no long range order in the arrangement of particles. Perhaps it may have short range order, and certainly they have isotropy. A pseudo solid is isotropic. It has same properties in all directions like talcum powder. It is soft in whatever the way you hold it, and of course pseudo solid is not having any cleavage pattern. That's different. Now our interest is in the solids. We agree upon that there is a particular pattern in the arrangement of particles. We assume that the particles in solid are spherical at the moment, and they are arranged in three dimensions. In this arrangement it appears that there is a repeating pattern. The repeating pattern may have a specific shape, and this type of repeating pattern you can observe. For example, in some solids this arrangement is having, clearly you can see three axial lengths: length 1, length 2, length 3. These axial lengths may be called as ABC, and of course they have definitely three angles, and these angles are called alpha, beta, gamma. This repeating pattern, actually the particles are arranged like this in three dimensions. It looks like a simple cube, for example. The three-dimensional arrangement of particles which is repeating is called as a unit cell, and the unit cells are many types. There are 7 fundamental types of such crystal systems we have. In that, the simplest one is cubic system. In a cube, all the three axial lengths are identical, and all the three axial angles are equal to 90 degrees. And here you can see particles are arranged so that they appear to be as if they are touching. This is a cubic system. In a cubic system, where A is equal to B is equal to C, alpha is equal to beta is equal to gamma, I can see that this is the repeating unit, and in this repeating unit, these particles are situated in these corners. They are actually looking as if they are touching each other. And now, in this arrangement of particles, if you see, this is called edge length, and each edge length corresponds to 2r, because if the radius of the particle is r, means edge length is equal to 2r. Particles are confined only to corners where edge length is equal to 2r is called as a simple cube, for which of course A is equal to B is equal to C, alpha is equal to beta is equal to gamma is equal to 90 degrees. Sometimes you can also see an arrangement where in a cube these particles which are arranged are not only confined to corners, but they are also there in the face centers, because in a cube it has 6 faces. If the particle is there also in face center, mind you, always these particles exist as if they are close back, they are touching each other. You can see that here these particles, here this particle, they arrange themselves as if they are touching. Right. And of course it has 6 faces: one face, second face, third face, fourth face, like that you can put. Okay, let's use this color. and this is another face, this is another face. So now let us focus on this. If this is called A, if this is also A, because this is a simple cube, and now according to Pythagoras theorem, this diagonal is equal to root 2a. Now in the face centered cube, root 2a is equal to 4r. It means the radius of 4 particles is equal to root 2a. Now a is equal to 4r by root 2. Right? It also implies r is equal to root 2a by 4, where r is equal to radius of the particle which is making the crystal lattice. A is called edge length of the crystal system. Now in this array, it continues to have millions of unit cells like this. In this arrangement, one can see what is the nearest neighbor distance to this particle. Nearest neighbor distance to this particle, anywhere you can see, is double the radius. 2r is equal to nearest neighbor distance always. Nearest neighbor distance can be worked out from this relation as root 2 by 4a into 2. That is equal to root 2 by 2a is the nearest neighbor distance in what? In a face-centered cube. If the particles are confined to corners as well as face centers, I call it as face-centered cube. If particles are there in corners and also in body center, I call it as body centered cube. In a body centered cube, if you draw a diagonal like this, you would see that this particle, this is starting here, it is touching here. So how many particles are touching this? 1, 2, 3. The body diagonal can be shown to be equal to, this is A, this is root 2a, just now we have seen, and you are looking at this. This is A, this is root 2a. Then again applying Pythagoras theorem, we can see that body diagonal is equal to root 3a. In a body centered cube, root 3a is equal to 4r. Therefore a is equal to 4r by root 3. Or radius is equal to root 3a by 4. And now nearest neighbor distance in this case is equal to root 3 by 4a into 2. That's equal to root 3 by 2a. So this is how we work out these simple systems. In the next video we see how efficient, how much space is actually occupied and how much space is wasted in these cubic systems. Thank you.